Hi everyone, very good evening. So we are going to start with this session on the topic atoms today. So we'll start with the session, guys. So the atoms chapter, right, this is in a way more like an as I said, it's like a subset of the chemistry chapter. You will have a structure of the atoms. So in this, what we are going to be mainly covering is we look at the discovery of the fundamental particles, starting from the Thomson's experiment, and then the discovery of protons and neutrons. That is the first part of the chapter. Then we look at the Rutherford's experimental observations and the Rutherford's model of the atom. Then we'll talk about the understanding of spectral studies of particularly hydrogen and hydrogen-like species. Then we have one of the successful models of the atom that can explain the spectral studies of hydrogen and hydrogen-like species, Bohr's model. Of course, the Bohr's model you would probably be aware, it is only for what? It is only for the hydrogen and hydrogen-like species. Then we'll also touch upon the X-rays and laser. So this is the broad coverage of the chapter. So as I said, right, this is like a subset of so what you have in chemistry chapter. So we'll start, guys. We'll start with the discussion. So the first part in today's class, right, we are going to be mainly talking about the theoretical aspects of how the fundamental particles have been discovered. It's not a one-day activity. It has taken a lot of years for different people in different experimental manner. They were able to find out what are the particles that are present inside the atom. So these particles we'll call as what? Subatomic particles. But if you look at where it all began, so it began with the atomic theory which is proposed by John Dalton. So John Dalton, he is a chemist and he is also a physicist and he is also a meteorologist. Means he will also be looking in terms of the weather aspect. So he proposed what is famously called as the atomic theory. So in which he said matter is made up of smallest indivisible particle. So what he proposed is matter is made up of smallest indivisible particle, and that's why the name atom. So A is a negative prefix, means tome. Tome basically means to cut. So atom means which cannot be cut any further. So that's the genesis of the atom. And he gave certain postulates in the Dalton's atomic theory. He gave some postulates saying atoms of same element will be of similar nature, atoms of different elements will be of different nature, and so on and so forth. But the question people had was, why atoms of Gunavati and Rachel? Hi. So why atoms of different elements are different in terms of, like say for example, if you have an iron atom, that is fundamentally different from a gold atom, which is totally different from a silver atom. So why atoms of different elements are having different characteristics, and why all atoms of same type, like we get iron atoms from different sources, all the iron atoms are of the same type. So why is it that different elements atoms, they have different properties, and same element atoms, they have same properties? So there must be something there inside the atom, and this is the quest that people had to understand what is there inside the atom. And through the efforts of different scientists, right, the classical understanding of atoms. So what we are going to study in our +2, right, is not the modern theory of atom. So what we are going to study is still the classical theory of atoms, which is proposed, at the very early stages. So we are not going to learn about the modern theory of atom. So modern theory of atom, we'll talk about, different set of particles, but the classical theory of atom, right, is mainly about the atom made up of essentially these three fundamental particles. What are these three fundamental particles? Electrons, protons and neutrons. So we'll see, how these particles are discovered and so on and so forth. But to give us a picture, right? So we have electrons which are negatively charged. We look at the relative charge as -1, protons identical but positive charge, different nature of charges. Electrons have got one type of charge and protons have got other type of charge. Neutrons are neutral, so they don't carry any charge. In terms of the representation, right, we use the symbol E minus or E to indicate electron. We will put a symbol P for the proton and N for the neutrons. What about the approximate or relative atomic mass? If you take the mass of proton, which will be almost equal to mass of neutron, if you take it to be 1, then the relative mass of the electron will be what? 1 by 1836 times. Means if you look at the comparison, right, mass of electron will be what? Mass of proton by 1836, and mass of proton and neutron will be almost similar. So we can see below the actual numbers are given. In terms of AMU unit, right, AMU is what? Atomic mass unit. It can also be called as what? Unified mass. Okay. In terms of AMU value, what is the mass of proton? 1.007276471. I mean, we don't need to remember up to those many number of decimal places. But look at the neutron. That's almost same but slightly higher. So for all practical purposes, we can take the mass of neutron to be equal to mass of proton, but it will be slightly higher. Okay. And we can see the mass of electron accordingly what? It will be lesser. How much times? It will be 1836 times. In terms of the actual SI unit of mass, kilogram, right? What is the mass of electron? This is something that we have been using it, 9.1 into 10 power minus 31. And mass of proton and mass of neutron, right? Almost it will be equal to what? 1.67 into 10 power minus 27 kgs. So this is about the mass of the proton and mass of the neutron. Coming to the charge part, right? Electron will have a negative charge, proton will have a positive charge. But what is the charge value? 1.6 into 10 power minus 19 coulombs. So this is what we have as the understanding of the subatomic particles, the particles present inside the atom. Now what we will be learning in this chapter is we will see how these particles are first of all discovered, and then we will also understand how scientists have tried to explain the arrangement of these particles inside the atom. And that is essentially the basic concept of atomic model. So what is the basic idea of atomic model? It talks about how the constituents of the atom. So even before knowing that there are these subatomic particles, generally what people used to say is the constituents. So whatever is the constituents of the atom, right, inside whatever is there, how that is arranged is what we will be learning in the atomic model. So the first of these subatomic particles to be discovered is electrons. So initially, during the discovery time, right, the electrons are given a name which is called as cathode rays. So this is famously performed by the scientist. So the scientist who is on the left side, right, we already discussed about this scientist, J.J. Thomson, and the person who is on the right side, already we discussed in the previous chapter, he is G.P. Thomson. So J.J. Thomson is a scientist who's been credited for the discovery of electrons, where he said electrons will be negatively charged particles. His own son later proved it otherwise. He proved through experimental observation that electrons are actually having the wave characteristics. So we already talked about it in the dual nature chapter. Anyway, so let's come back to what J.J. Thomson actually did. So J.J. Thomson, he performed this famous cathode ray tube experiment, which is also called, by the way, as discharge tube experiment. What is the other name for the cathode ray tube experiment? It can be also called as what? Discharge tube experiment. What is this discharge tube experiment? We'll have an gas tube where the density of the gas, which is generally quantified in terms of pressure. More density means what? More pressure. Less density means less pressure. I'm sure you would be learning about this in the gaseous state chapter. So what is it? The equation is what? Pm is equal to dRT. Pressure into molar mass of the gas is equal to what? Density into R into temperature. If you fix temperature and nature of the gas, right, the pressure will be directly proportional to density. So we take low density gas or gas at low pressure, and In this, right, we'll keep a electrode setup. We'll have a cathode will be what, negative electrode, and we'll have an anode will be positive. So anode can be kept in different locations. So here at normal voltages, right, nothing is generally observed. But if you take the voltage value to a very high level, so typically we talk about in the range of 10,000 volts, then what is observed is blue rays. They have been observed to emerge from the cathode, and they are moving towards the anode. So these blue rays, right, they emerge from the cathode, and we'll talk about the properties of the cathode rays in a while. But just to talk about the observation, right, how it has all happened. So the idea of electricity is quite known to people back then, and to understand what is there inside the atom, he performed this cathode ray tube experiment where he took a low density gas, or a gas at low pressure, basically saying what, the number of gas particles here will be less, the number of gas atoms, right, will be what, less, because we are taking a very less density. And at high voltage, what is observed? It is observed that there are these blue rays which are appearing to be emerging from the cathode. So we have to be very clear in terms of the wordings that are used. So the exact wordings that they have mentioned is that these cathode rays, they appear to be emerging from the cathode. Okay. So it is not said that they are actually coming from cathode, they appear to be emerging from the cathode. So that is the description of the cathode rays, and hence they are called as what, cathode rays. Since they appear to be coming from cathode, they are called as cathode rays. Now let's talk about the properties of the cathode ray. So this is the observation that he did. If you look at the properties, right, so cathode rays, first of all, they are coming at right angles to the surface of cathode, and they are moving in straight lines. So they are coming at right angles to the, so if we have a cathode, right, we have a cathode, and they are coming what, normal to the cathode surface, and they are moving in straight lines. And another interesting thing is they produce the phosphorescence effect on certain salts like zinc sulfide. If you, on the other end of the glass tube, if you keep zinc sulfide salt coating, right, what you will be able to observe is phosphorescence. And when they impact a glass, they are creating fluorescence. So what is this phosphorescence and fluorescence? These are chemical terms actually. So if you look at any salt, right, zinc sulfide, we heat it, okay, so where it doesn't undergo combustion, there should not be a combustion, we just heat it, and there will be no melting also. So there will be no combustion of that salt, and there will be no melting. So we heat it till there is no combustion and there is no melting. In this case, right, the salt will be emitting light, and this effect is what is called as phosphorescence. Salts generally, when you heat them without allowing them to undergo combustion and also without allowing them to undergo melting, right, they can create this radiation, or they can emit the radiation. This is typically called as what, phosphorescence. So we can see here on the other side, right, this is the one that you're seeing in the green color, right, this is basically what, the phosphorescence. This is the phosphorescence of the zinc sulfide. And the other thing that we are mentioning is fluorescence on the glass. So fluorescence is a technical term that we use. Generally, if you have materials like glass or anything, when we make a radiation to fall on them, they absorb the heat and they radiate a part of it. Means when they are giving out the radiation, typically what happens, a light of lesser energy is going to be emitted. So we can say light of lesser frequency or higher wavelength, because they absorb a part of it, and when they are radiating, right, they will be radiating only a lesser amount of energy. So a less frequency photon will come out, or a higher wavelength photon will be coming out. So we can see over here, this is what is the blue color pitch, we are able to observe it right on the glass. So this we can say is what, it is the result of the fluorescence. So these are the immediate observations that people are able to do, because immediate means what, we see based on the simple visualization. So whatever people are able to observe, we see that the rays are coming what, normal to cathode plate, and they are moving in straight line. Second thing is what, they are able to create, if you are keeping a zinc sulfide screen or any salt screen, they are able to create what, phosphorescence, and on the glass plane they are able to create what, fluorescence. So these are the immediate observations. Then looking at what else the cathode rays are able to create. The cathode rays, they blacken photographic plates. The photographic plates, right? They will blacken the photographic plates. It is because of the the chemical reaction that happens on the photographic plates. We'll see what actually happens, because cathode rays, later we will see that these are nothing but what? Electrons. And when the rays pass through a thin sheet of metal, right, they will go through the metal. So if you have a very thin sheet of the metal, they will simply pass through. But if you have a really thick sheet of metal, they will be not able to penetrate and they will cast shadow. So cathode rays, if you have a very thin metal sheet, means they will be able to penetrate through. They will pass through. But if you have a very thick sheet, right, then the cathode rays cannot penetrate and they will be casting shadow. And this is something that in the discussion of dual nature chapter we talked about it. These cathode rays, right, they produce X-rays when they strike a metal. Like I hope you guys are able to recall, we have looked at this diagram also. So from the cathode, if we have cathode rays being produced and when they are made to impact on the anode. So this is what we call as the target metal. So the anode is what is called as the target metal. Of course, in this chapter we'll discuss in detail about the production of X-rays, etc. So they will be able to produce the X-rays when they are impacting a target metal. Okay, and we have seen that target metal should be having typically high melting points, because a lot of heat is going to be produced in the process. And when these rays are passing through gas, right, they have the property of ionizing the gas. So again we will see why they are able to ionize the gas once we finally understand that these are nothing but what? Electrons. And when they are made to fall on a substance, right, because they are carrying energy with them, they will be able to create the heating effect. So they will be able to heat the substance on which they are falling. And the last point here is a very important one, because this has changed the perception of people, because till now, right, people were thinking that the cathode rays are actually ray, because the word ray itself, right, ray is used in the context of what? Light. We'll say X-rays. The word ray is used in the context of light. But this point, right, has changed the perception of what are these cathode rays. If you look at these cathode rays, they rotate a light wheel placed in their path. Means if the cathode rays are coming like this and we keep a light wheel in the path, right, what they are able to achieve is they are able to rotate the light wheel. And this basically shows what? Because rotating a light wheel means they are able to create a mechanical impact. Rotating a light wheel means what? They are able to create a mechanical impact. And this basically indicates what? This indicates that these, whatever the cathode rays, right, the composition of cathode ray must be what? It must be material particles. Then only they can create the mechanical impact, which means what? They must be particle having mass and which are moving with a particular velocity. That's why they are able to create the mechanical impact. So this has changed the perception about the cathode rays. Now people have come to the understanding that cathode rays are not actually a form of light rays, but they are actually what? Particles. Since they are able to create the mechanical impact. Okay. And digging further into the properties, right, once it is understood that these cathode rays are particles, since they appear to originate from the cathode and they are moving towards the anode, it is quite clear that these must be charged particles. And since they are appearing to move away from cathode, right, what is the expected charge on them? The expected charge on them is negative. But this is verified by the effect of magnetic and electric fields. So how people were able to verify this? That these are actually charged particles by the effect of magnetic and electric fields. So if you have a beam of charged particles, remember we have discussed this in the moving charges and magnetism chapter. Okay, so in moving charges and magnetism, right, if we have a charged particle Q which is moving with a velocity v in a magnetic field B, then what is the force acting on the charged particle? Q into V cross B, or QVB sin theta. Means what? The charged particles which are moving will experience a force when they are going through a region where there is a magnetic field. And you can see we have two visualization here. Let us focus on the first one. So what is this first one? This is actually the beam of cathode rays coming, and we can see when you move the magnet through that place, right, what is happening? The beam of rays is actually bending. Why is it? Because of the magnetic field. So the magnetic field is able to deflect. It is able to deflect the cathode rays. Similarly, I'm not sure, nowadays people are not used to these TVs, but the previous generation, right, probably when your father and mother, they were watching TVs for the first time, right, there used to be these kind of TVs, the TV boxes, okay. So TV boxes, it works on the cathode ray concept, okay. So the screen, right, it works, on the idea of the cathode rays. Maybe, when we have some time, we'll discuss about how these TVs used to work. But here, it's not very much required for us, but just understand that, these TVs also work on which principle? The principle of cathode rays. So you can see, if you are bringing any strong magnet close to the TV, right, what is happening? The entire picture is getting deflected. It is because of what? It is because of the deflection of the cathode rays by the magnetic field. And this happens, okay. So, and this is happening in the case of the cathode rays also. Means what? These must be charged particles. And the same thing is also verified. So when we set up an electric field, right, again it is observed that these cathode rays are getting deflected by the electric field. So generally we know that the charged particles, right, normally itself charged particle, if there is a charged particle Q, means in electric field E, what will be the force acting on the charged particle? Q into E. So charged particle, whether it is at rest or in motion, it will experience force because of the electric field. But a charged particle in motion only can experience the force because of magnetic field. Only the moving charges can experience force because of the magnetic field. So this, was verified, and it is now established that what are these cathode rays? They are actually negatively charged particles. Now the idea is basically, where are these particles coming from? And when the charge by mass ratio, so we'll see how this value, the charge by mass ratio, right, this is also, by the way, called as the specific charge. This is also called as what? Specific charge. So different gases, because we said the cathode ray tube is having a gas, right? So if we change the gas, maybe for some time we may use hydrogen gas, sometime we will use nitrogen gas, then oxygen gas. Different gases can be used inside the cathode ray tube. So if you use different gases, then the cathode rays that are coming because of these gases, right, all of them were having the same value for the specific charge. We'll see, how the specific charge value is calculated. But here, when they have actually performed the experiment by using different gases inside the discharge tube, the specific charge value for the cathode ray particles was coming to be what? Same. Means the conclusion is what? So these particles which are negatively charged must be present inside every atom. So whether it is a nitrogen atom or hydrogen atom or oxygen atom, these negative charge particles must be present in every atom. So this is the conclusion that people have come to when the specific charge value was coming same, irrespective of the gas used in the discharge tube. And the other thing is, if we don't use any gas, means we completely evacuate, then no cathode ray was produced. So this is the other checkpoint, right? Like we are seeing that okay, different gases are used, we are getting the same value for the specific charge. Means the conclusion is what? Okay, these particles must be present in all type of atoms. But are they really coming from the atoms, or they are coming from somewhere? How do we check it? If we completely evacuate, means not even that small density of the gas is there, totally evacuate it by using the vacuum pump, then there are no cathode rays observed. Means it is clear that these cathode rays are the negative charge particles are present in every type of atom, and they are coming from the atoms. And J.J. Thomson, right, he was able to discover the specific charge value for this electron, and he has used the word electron. The specific charge value is found to be what? 1.76 into 10 to the power of 8 coulomb per gram. We don't need to remember this value, but let me tell you how this specific charge value is calculated. If you look at the deflection of the charged particles, right, let's say there is a charged particle Q which is moving with a velocity v. If it is moving in a direction to perpendicular to magnetic field, then it will be taking a circular path. So we have learnt about it in the moving charge and magnetism chapter. what is the radius of the circular path? R is equal to mv by dq. So look at this from here, right? The q by m value will be equal to what? V by b into r. Because v is the velocity with which we are moving the charged particles, that is already there with us. B is the magnetic field that is created in the place, and r is the radius of the circular path that the charged particles are taking. This is a geometric property. So on the RHS, right, we can see everything is what? Measurable property. And in the LHS, what is there? Q by m. This Q by m is basically what is called as the specific charge. And since for electrons, right, the symbol for the charge is used as what? E. So that's why we use the word E by m. So that is how the specific charge value was calculated. So the specific charge value is what? 1.76 into 10 to the power of 8 coulomb per gram. So this is about the discovery of the electrons. And once the electrons are discovered, then the question was what is the composition of the atom, because it is clear that inside every atom these negative particles are there. And the idea is, if you look at atom as a whole, right, we don't see any charge transfer. Means what? It is clear to people that atom is what? Neutral. Atom totally is what? Neutral. Then there must be an equal amount of the positive charge, which is of course not coming out of the atom, because as per the Thomson's experiment, what he was able to see is only the negative particles coming out. Means there must be positive charge which is not able to come out of the atom. And based on this simple idea, right, he came up with a model which is popularly called as what? The plum pudding model of the atom. Okay, so I've just shown what is the plum pudding, but yeah. So what is this plum pudding model of the atom? It is based on the idea that there is a positive cloud. So there is a positive cloud inside which the negatively charged electrons, right, the negatively charged electrons are embedded. The negatively charged electrons are embedded in a positive cloud. Okay, and so he proposed this in 1904, and this is one of the very short-lived atomic models. We'll discuss about it, why it is a short-lived. But yeah, so the idea is what? If you look at the plum pudding model, right, it's basically based on the idea of a plum pudding, where we have the bits of plums which are surrounded by the matrix of pudding. Okay, and we can also call it as what? The watermelon model. So where we see that the positive cloud is like the red color part, and the electrons are embedded like the seeds in a watermelon. So this is the J.J. Thomson's model of the atom, because it is based upon one idea that there must be an equal amount of positive charge inside the atom which is not able to come out, and that is the reason why he is able to come up with this idea of a positive cloud in which the negative particles are embedded. But we said this is one of the short-lived models of the atom. Why? Because it is not just that, okay, there are advancements happening in terms of the understanding of the atom in one branch of physics or chemistry. Parallelly, there were other studies performed, especially on the charges and charged particles. Okay, so one of the important properties of the charge is the idea of charge cancellation or charge nullification. So what is this charge cancellation or charge nullification? I'm sure you would have covered this in the electric charges and fields chapter. So it's a very basic property of the charge. If you have a positive charge and negative charge, we bring them together, we make them to contact. Then what is going to happen between the two charges? They will cancel each other, they nullify. Now here J.J. Thomson's model is saying exactly the same thing. We have a positive cloud into which the negative particles are embedded, means they are in contact. Now if they are in contact, what must be happening? There must be charge cancellation. There must be what? There must be charge cancellation. If there is a charge cancellation, then there should no longer be a positive cloud, because if the charge is cancelled, right, there should no longer be a positive cloud and there will be no more negative particles. because they both are cancelling the charge. But atom, we are able to see it existing, because always we will see that there are negative particles and there is a positive part. So the coexistence of Thomson's model said about what? Coexistence of the positive and negative charge. So the model is based upon the coexistence of the positive and negative charge. And this is the drawback of the Thomson's model, because one of the basic properties of the charges is what? That if positive charge and negative charge are coexisting, then they will be cancelling the charge. That's what we call as the nullification of the charge. So this is a very glaring drawback with the Thomson's model, and that has made other scientists to start working on how else the positive charge, because it is established that atom totally is what? Neutral. How else the positive charge can be present inside the atom. And while all this is happening, right, the understanding of the electrons also was not fully complete, because Thomson was able to only find out the specific charge value, E by M value. The completion of understanding about the electrons happened because of the Millikan's oil drop experiment. So Millikan, he designed a setup using which, right, he was able to find out what is the charge on the electrons. And once he is able to find the charge, means already we know the E by M ratio. Once we are able to find the charge, means we can find the mass also. So that has completed the understanding of the electrons. So the Millikan's oil drop setup is basically, you have an atomizer which will spray oil droplets. Okay, and these oil droplets, they will be bombarded with a beam of charged particles. So the oil drops will be having a charge, and they will be now made to pass through region between two charge plates. We can see there is a positive charge plate and there is a negative charge plate. Means in this region, right, so while the oil drops are coming down, the oil drops will experience gravitational force mg downwards. The oil drops will experience a gravitational force of mg downwards. So the electric field in this region, right, is set up in such a way that the force because of the electric field will be upwards. The force because of electric field will be what? Upwards. So if you see, there is a positive plate and negative plate. Field will be like what? Field will be in the direction from positive plate to negative plate. But electrons are negative charged particles, right? How they are going to experience force? They will experience a force in the direction opposite to electric field. Because a negative charge, say for example, if the field is towards right side, negative charge will experience a force towards the left side. Why? Because what is the formula? F is equal to Q into E bar, right? If the charge is negative, means the direction of the force acting on the charged particle will be what exactly? Opposite to field direction. Now since the field is downwards, the electrostatic force acting on the oil drops, because oil drops are carrying the charge, the electrostatic force acting on the oil drops will be acting upwards. And while the oil drops are coming down, they can be viewed in the chamber. So this is the viewing chamber where we can make the oil drops to be more visible with the help of some artificial lighting, etc. But yeah, so we can view the movement of the oil drops with the help of a microscope. So this is the setup. So we will see how he has worked out a method to find the charge on the oil drops. But this is the basic setup that he has created. And the working of this is, while these oil drops are actually falling down, right, the observation of the oil drops is such that the oil drops which are having a constant velocity, the oil drops having constant velocity means the ones that will experience a force balance. So there will be two forces acting on the oil drops. One is the weight and second is the force because of the electric field. So these two forces, if they balance, then what is going to happen? Those drops are going to be coming with a constant velocity. So the microscope is used to observe the particles which are coming down with a constant velocity. So if you look at the idea of the Millikan setup, right? So if these oil droplets are falling to the bottom, then they will pass through the region between the two plates where we are creating the electric field. the electric field is going to apply a force on the oil drops exactly in the opposite direction. So if say for example Q is charge on the oil drop, then the electric field is E in the place, Q into E. Numerically Q into E will be equal to what? Weight, M into G. In this, the mass of the oil drops will be known, and acceleration due to gravity is of course known to us. E is the electric field that we are setting up. So this is also known to us. So what is the only unknown variable here? Q value. Q value is equal to what? Mg by E. What is the Q value? Mg by E. So by using the calculation of the Q value from the experimental data, what he observed was all these Q values, right, they are coming as a multiple of this number, 1.6 in 10 power minus 19 coulomb, okay, or 3.2 in 10 power minus 19 coulomb, or 4.8 in 10 power minus 19 coulomb. So all the charge values on the oil drops, right, they are coming as a multiple of this number. Then the conclusion that he had is that the charge on the oil drop, the smallest value of the charge, which is 1.6 in 10 power minus 19, of course, I mean, the charge will be negative in nature, but the value we are talking about, the smallest of these values, right, is going to be the charge because of one single electron, and that is how he was able to find out the charge of an electron, which is what we call as the basic charge. So the Millikan's oil drop experiment, right, he was able to find out what is the charge value on the electron, and this value, right, using this value, since already we have the E by M ratio, the value of mass of the electron was also derived. So mass of the electron is what? 9.1 in 10 power minus 31 kg. I mean, we don't need to remember up to like lot of decimal places. Generally when we talk about the charge means what we'll say, 1.6 in 10 power minus 19. Mass of electron means 9.1 in 10 power minus 31 kg. So this is how we'll express the values. We will not go up to like 3 decimal or 4 decimal places. We'll just keep it up to just 1 decimal place. So this is the Millikan's oil drop experiment where he was able to find out what is the charge of the electrons. So it's again just to quickly summarize, it's a simple idea that as these oil drops are coming down, they will experience weight downwards and the force because of the electric field upwards. From the balancing of the two, we will find what is the charge value on the oil drop. So if all the oil drops are observed, right, we look at the charge value of the oil drops, the charge values are coming as a whole number or whole number multiple of this smallest value, 1.6 into 10 power minus 19 coulomb. So this is what is then identified as the smallest possible charge, which is the charge of one electron. So this is the Millikan's experimental method. Then the Millikan's method was able to summarize the understanding of electron, but still the question is how the positive charge is existing inside the atom. The discovery of anode rays or canal rays is the one that has led to the understanding of another subatomic particle which is there inside the atom, and that's called as the proton. So Goldstein, right, he is the scientist who has been credited for the discovery of the protons. Now he got a very simple idea that maybe in the discharge tube setup, right, while Thomson was observing cathode rays which are bright rays. Cathode rays are what? They are bright rays. Like the way normally if you look into the sky, right, you see a bright star, and adjacent to that there are some dull, in terms of the, the shining property we're talking about. Adjacent to that there are some dull stars. Then we will not be able to notice those dull stars. Our focus will be only on the bright color ones. So his hypothesis is that maybe while the experiment was observing on cathode rays, there may be another set of rays which are moving exactly in the opposite direction, but we are not able to see them because they are not bright. So with this idea, right, he started looking for the possibility of anode rays. So why the word anode rays is used? It is used because of the idea that these rays must be traveling from the anode side. Just like the way cathode rays are traveling from where? They appear to be traveling from cathode, right? They appear to be coming from the cathode. So these rays will appear to be coming from the anode side. That's how the word anode rays is coined. And the discharge tube setup, right? Since this is the anode and this is the cathode, in this region, right, already there are these cathode rays present, which are very bright, because cathode rays are what? Bright rays. We will not be able to observe them in this region. So in this region we will not be able to observe if at all there are other rays which are coming from anode, right, we will not be able to observe them, because there are also the cathode rays, bright rays. So what he came up with is an idea of perforated cathode. So what is this perforated cathode? So if we have the anode rays at all coming, then as they come to the cathode, right, because they will start from anode and they will approach towards the cathode, right, if you make some holes, simply holes in the cathode, then they will be able to, some of these rays will be able to pass through the holes. And in the back side of cathode rays, back side of the cathode, here cathode rays will not be there. The back side of the cathode rays will not be there. So if at all there are any of these rays, right, only those rays are going to be present on the back side of the cathode. So this is the idea that Goldstein has used, where he has done essentially the same setup. Whatever the setup that J.J. Thomson has used, Goldstein also used the same setup. He has used the discharge tube setup, but the only modification is what? He used a perforated cathode. And when he's observed on the back side of the cathode, right, what he found is there are some rays which are passing through the holes, and they are passing basically in direction opposite to the cathode rays. And this is, the discovery of the anode rays. So anode rays are discovered on the back side of the cathode, because in the region between the two electrode plates, right, since the cathode rays are bright, the people were not able to observe the existence of the anode rays. But using a perforated cathode setup, he was able to see that on the back side of the cathode ray, there are these anode rays being observed. And where these rays must be starting, the rays must be appearing to come from the anode side. But only on the back side of cathode we are able to observe them. Why? Because these may not be that much bright color rays. And looking at the properties of these anode rays, the anode rays must be what? Positively charged. Since they are moving in the opposite direction to cathode rays, these must be what? Positively charged. And the positive charge is either equal to or whole number multiple of the charge on electron. The charge on the the anode rays, right, is positive. And what is the value of the charge? It is observed that this charge value, right, is either equal to the basic charge, value of the charge of electron, or the whole number multiple. So this is the observation in terms of the charge. And if you have a hydrogen gas filled in the discharge tube, right, the positive charge on the anode rays is exactly equal to the negative charge of electron. Means what? Here the charge value is depending upon the type of gas used. The charge value is not same. The charge value is depending upon the type of the gas used. Here what is observed is, if you take hydrogen gas, then the positive charge value on the anode rays is exactly equal to how much? Exactly equal to the negative charge on the electron. See, in hindsight, right, we will now be able to understand why it is happening. Because if you look at a hydrogen, since we know today that hydrogen will have what? It will be having a proton and electron. This is something that we know today. Now if it is losing electron, the hydrogen atom is losing electron, what is remaining? The remaining entity is nothing but proton. If hydrogen atom is losing electron, means the remaining entity is what? Proton. And the charge on the proton will be exactly equal to what? Charge on the electron. And the mass, right, is just less than the hydrogen atom mass. Because between the two particles, I am assuming that we already have some understanding about the protons and electrons. Between the two particles, right, the proton is a heavier particle, electron is a lighter particle, proton is a heavier particle. So we can see that the remaining mass will be what? Just mass of proton. So the mass of proton is found to be what? Just less than the mass of hydrogen, and the charge is same. The numerical value of the charge is same as the numerical value of the charge an electron. So this is what is observed in case of the anode ray tube experiment performed by having the hydrogen. And the characteristics of these anode rays, right? Cathode rays, I mean whatever gas that is taken, the specific charge value was coming same. This is the observation that was happening in the cathode rays, and that has led to the conclusion that these cathode ray particles must be present in all the type of atoms. But in case of the anode rays, right? Anode rays, by the way, I mean I'm not reiterating the word. Anode rays can be also called as what, guys? They can be also called as canal rays. Anode rays can be also called as what? Canal rays. Okay. So the properties of these anode rays, they vary depending upon the gas that is used. If you look at it, why the anode rays are nothing but the cations of the respective gases. Because what is anode rays? I mean today we will be able to understand what are these anode rays. Anode rays are what? If we have say helium atom which is there inside the gas discharge tube. If it is losing electrons, helium can potentially lose how many electrons? It can lose 2 electrons. The remaining thing will be what? Helium 2 plus ion. Those will be the anode ray particles of the helium anode ray discharge tube experiment. And if you talk about hydrogen, right? I mean we are assuming that we are talking about the protium isotope of hydrogen where it has got 1 proton, 1 electron. If it is losing 1 electron, means the remaining thing is what? H plus. So the anode ray particles are nothing but what? H plus or simply proton. So these are the anode rays in case of the hydrogen gas experiment. So the properties of these anode rays, right? They are not constant. They will change. They depend upon the nature of the gas used in the tube. And just like the cathode rays, right? Since they also have a charge, they will also get deflected because of the electric fields and magnetic fields. But remember, we have discussed about this in case of moving charge and magnetism chapter. If you look at the force acting on charged particles because of electric field, what is the force formula? Q into E. Positive charged particles, they will experience force exactly in the direction of the field. Negative charged particles will experience force in the opposite direction. Similarly, on a moving charge, what is the force because of the magnetic field? Q into V cross B. Here also, the direction in which positive charged particles experience a force will be exactly opposite to the direction in which negative charged particles will experience force. So, based on the deflection, right, it is observed that the charge must be what? Exactly opposite nature. And the other thing is the deflection amount or the effect of electric field and magnetic field can also give an idea on what will be the mass of the particles. Because let us say, for example, we talk about the radius of the charged particle which is revolving in a normal magnetic field. What is the radius formula? R is equal to mv by bq. R is equal to what? mv by bq. Now looking at this R value, right, we can comment on what will be the mass of the charged particles. So it is observed that the mass of the positive rays is much greater than the mass of the electrons based upon the deflection properties. Okay, so this is about the broad properties of the anode rays. And based upon these observations, right, so what are the main observations of the anode rays or canal rays? The canal rays will have positive charge, and if the relative charge of the cathode rays is taken as -1, right, then in most of the cases what is the observed charge on the anode rays? It is +1, but sometimes it can be +2, sometimes it can be +3. Mass value is definite, the E by m value is also definite. Okay, whereas in the case of the canal rays, the E by m value also depends upon the nature of the gas, and mass also depends upon the nature of the gas. Why? Because the canal rays are nothing but the cations of the gas atoms. Because once you have an atom, it has lost an electron, the remaining part is going to be what? Cation. How the cation is going to move? So if you have a anode here and a cathode, So cations are what? Positive charge, right? How they are going to move? They'll move away from the anode. They will be moving away from the anode and they will move towards the cathode. So that is why the word the anode rays is given to them. But what are these particles which are there making up these anode rays? These are the cations of the respective atoms. Once they lose electrons, the remaining entity is what? Cation. That is the positive charge particle. So that is the reason why their mass depends upon what is the nature of the gas, and their specific charge value also depends upon what is the nature of the gas. So based on these observations, right, the idea of protons has been proposed. So the proton is proposed as the subatomic particle which is a fundamental constituent of all matter, and the mass of this is slightly less than the hydrogen atom mass, because this is observed in the case of what? In the case of discharge tube experiment performed on the hydrogen gas. So the hydrogen gas, when discharge tube experiment is performed, the charge value is numerically equal to charge of the electron. Mass is what? Mass is slightly less than the mass of the hydrogen atom. So this fundamental particle, which is having same amount of positive charge, magnitude wise equal to the charge of the electron, and mass is slightly less than the mass of the hydrogen atom. This particle is called as what? Proton. So this is how the discovery of proton has happened. And once the discovery of protons has happened, now it is clear to people that inside the atom there are these two types of particles. One is protons, which are positive charged, which will be heavier particles, and they will carry the same amount of charge as that of the electron but opposite nature. And there are lighter particles, electrons, which have the same charge as the protons but mass wise they will be very light. So this is about the understanding of what is there inside the atom. And then there were further studies done especially by scientists like Rutherford, based upon his observations of famous experiment. We will see the Rutherford's experiment also. He was able to propose a model of the atom, which is considered quite successful until some drawbacks were found in that. But while this is happening, right, the third subatomic particle was still to be discovered. In fact, if we look at the timeline, right, Rutherford, the existence of the neutral fundamental particles, he predicted that inside the atom there could be these neutral fundamental particles in 1920. After almost like 12 years, right, Chadwick, so he basically discovered the existence of neutrons. So Rutherford, while he was proposing about his atomic model, he predicted the existence of the neutral particles to support the coexistence of all the protons. So we'll see when we go to the Rutherford's model of the atom. He predicted that there could be the neutral particles inside the atom, but it was not experimentally proven, and it was experimentally discovered by Chadwick when he was bombarding the beryllium with alpha particles. He noticed that there is a radiation which is emitted which has got these following characteristics. The radiation, right, is highly penetrating, and the radiation is unaffected by the magnetic and electric fields, because the cathode rays are affected by the electric and magnetic fields. Anode rays are also affected by the electric and magnetic fields. So these radiation, right, they are not affected by the electric and magnetic fields, which means what? They must be electrically neutral, and they found to be having the same mass as that of the protons. The mass of these particles, right, was found to be almost similar to that of the mass of the protons, and these particles are called as what? Neutrons. So the name of the neutron, right, is given for the particles which are present inside the atom, which will be neutral and that have the same almost similar mass as that of the protons. And we denote this neutron by the symbol N, and when the beryllium is bombarded by alpha particles, right, it results in the formation of carbon, and as a result the neutrons will be emitted. So we will see this reaction when we go to the nuclei chapter, because we will talk about a lot of these type of phenomena. So this is the discovery of the neutrons. and the mass of the neutrons is almost same as mass of proton but slightly higher. So the definition of neutron is what? Subatomic particle which is a fundamental constituent of matter, mass approximately equal to the hydrogen atom, and electrically it must be what? Neutral. So this is what is called as a neutron. And we know that all the elements will have neutron inside the atom except one isotope of hydrogen, which is the protium. So protium has got a mass number 1, atomic number 1. Means what? Inside the hydrogen atom protium, you will have one proton and one electron. So there will be no neutron. This is the only element that does not have a neutron. So this is the discovery of the three fundamental particles: protons, electrons, and neutrons. So we discussed a lot of these theoretical aspect today, and in the next class we look at the Rutherford's experimental observations and his model of the atom, and then we'll slowly get into the Bohr's model and the other topics. Okay, so we'll see in the next class.